800 miles of fault, 346 years of silence on the southern section, 20 feet of accumulated slip, 40 million people living above it. This fault is called San Andreas. It runs through the full length of California, from the Salton Sea in the south to Cape Mendocino in the north. Two tectonic plates grind past each other along its trace at nearly 2 inches per year. The fault does not move smoothly. It locks. The energy builds. Eventually, it does not stay locked. The fault has 3 sections. Each one operates on its own cycle. Each one carries its own arithmetic. The northern section last ruptured in 1906. San Francisco burned for 3 days. 3,000 people died. The city that exists there now holds nearly 1 million residents, with 4 million more in the surrounding region. The central section last ruptured in 1857. The surface split for 220 miles in 90 seconds. 1 person died. The population of California at that moment was 400,000. Today, it is 40 million. The southern section last ruptured in 1680. No newspaper covered it. No federal agency modeled it. The land moved, the strain reset, and then the plates kept grinding forward at the same constant rate they always have. That was 346 years ago. At 2 inches per year, multiplied across 346 years, the accumulated slip on the southern section now measures 20 feet. That figure is not an estimate. It has been confirmed by Global Positioning System satellites tracking the plate motion in real time. Verified against the peat layers of a desert creek 80 miles north of Los Angeles. Cross-checked by a paleoseismologist who spent 13 years counting ruptures by hand. The number does not change with a new administration. It does not improve with awareness. It sits in the rock, adding roughly 2 inches per year, waiting for the one condition that releases it, which is the lock giving way. The United States Geological Survey rates the southern San Andreas as the highest priority earthquake threat in the continental United States. The 308-page scenario they published in 2008 did not call the next rupture possible. It called it certain. The only unknown is the year. The southern section has been silent since 1680, and that silence is the most dangerous number in American geology. The fault appears from orbital altitude. Images from the International Space Station reveal it as a long diagonal seam crossing the western edge of North America. 800 miles of fractured rock running from the Salton Sea in the south to Cape Mendocino in the north. Aviators navigating aircraft above the Carrizo Plain can mark it without instruments. Streams bend at right angles where the 2 plates have dragged the land past itself. Ridges are sheared clean. Alluvial fans are split down the center, one half carried northwest, the other left behind. The land has been showing this for 10,000 years. The physics behind it is different from a subduction zone. Cascadia, Sumatra, Japan. Those faults involve one plate sliding beneath another, diving into the mantle, compressing vertically. The San Andreas does something else. The Pacific plate moves northwest. The North American plate resists. The 2 surfaces meet at a nearly vertical angle and grind laterally past each other, like 2 boards being dragged in opposite directions with enormous friction. Geologists call this a strike-slip fault. There is no subduction. There is no diving plate. There is only horizontal motion, locked by friction, accumulating year after year at nearly 2 inches per year. That rate is constant. It does not vary with politics, or with weather, or with how many people have moved into the basin. 2 inches per year, every year regardless. The fault does not operate as a single system. It runs in 3 sections, each with its own history, its own last rupture date, and its own independent clock. The northern section last broke in 1906. San Francisco. The central section last broke in 1857. Fort Tejon. The southern section running through San Bernardino and down toward the Salton Sea last broke in approximately 1680. Each section can rupture without triggering the others. Each section has been accumulating its own deficit since the moment it last moved. That word, deficit, is the one that matters. When 2 locked surfaces cannot slide, the motion has to go somewhere. It does not disappear. The rock on either side of the fault deforms elastically, bending and compressing the way a board bends when you press both ends toward each other. GPS satellites now measure this deformation in real time, millimeter by millimeter, year after year. The numbers confirm what the geology already showed. The plates are moving. The fault is not. The energy is being stored. A subduction zone stores energy vertically and releases it upward, lifting the seafloor and generating tsunamis. A strike-slip fault stores energy horizontally and releases it laterally, tearing the surface of the land sideways in seconds. The danger is different in character, not in scale. The release is faster, shallower, and concentrated directly beneath the cities sitting on the trace. Small earthquakes, magnitude 3 and 4 events, expend only a fraction of a percent of what accumulates at a locked section. They do not drain the deficit. They do not delay the rupture. They are noise around a much larger silence. Slip deficit does not bleed off through small tremors. It accumulates in silence and releases in seconds. January 9th, 1857, 8:24 in the morning. The temperature at Fort Tejon sits near 52 degrees. The air is dry and still. Inside the mess hall, 48 soldiers wait for breakfast. Captain Edward Beale, post commander, stands in his office reviewing supply reports. Outside, sheep move across the San Joaquin Valley. The Carrizo Plain stretches empty in every direction. One rider moves along the valley floor on horseback, following a creek bed that has not yet moved. The ground begins to move at 8:24 and 20 seconds. It does not shake at first. It rolls. Witnesses spread across 300 miles will later describe the same sensation independently. A low, traveling rumble, moving from northwest to southeast along the line of hills, faster than a horse could run, faster than the sound itself could be explained. The fault opens behind the rumble. The rupture covers 220 miles in roughly 90 seconds. Trees uproot along the trace and braid their trunks across the widening gap. Streams reverse direction for nearly 40 seconds, then resume flowing on the wrong side of the break. In the Carrizo Plain, the rider watches the creek bed in front of him slide 9 feet to the right in a single motion. The horse refuses to cross. A surveyor named Albert Wilcox, working in the area, would later document an offset at Wallace Creek exceeding 30 feet. The land recorded the motion in the geometry of its own surface. Every stream, every ridge, every alluvial fan along the trace was rearranged in under 2 minutes. At Fort Tejon, the mess hall collapses. Adobe walls fall outward in sheets. Beale survives because he is standing inside the wooden command office, which folds but does not crush. He spends the next 6 hours pulling men from the rubble. In his official report, he describes the onset of the shaking with a phrase that seismological literature would repeat for a century. That the noise preceded the shock by several seconds, like a freight train running underground. Every adobe structure within 60 miles of the rupture is down by mid-morning. The shaking reaches Visalia, 80 miles north. Brick storefronts drop their facades into the street in a single second. In Los Angeles, then a town of fewer than 5,000 residents, the shaking lasts long enough for Father Anacleto Lestrade at the Plaza Church to leave the altar, cross the nave, and reach the door before the ground stops moving. The event is felt in Las Vegas, across the border into Mexico, and by ships 90 miles offshore in open water. Total dead: 1. A woman near the village of Reed's Ranch, close to present-day Gorman, killed when her home collapsed on top of her. The population of California in 1857 was approximately 400,000. The population along the rupture line itself was roughly 600 people. Today, the same trace passes through Palmdale, Wrightwood, and San Bernardino. Combined population in those communities alone exceeds 2 million. Within 50 miles of the fault line, 20 million more. In a different century, the Fort Tejon earthquake kills 100,000 people. In 1857, it kills 1. That difference is not geology. That difference is timing. The land was nearly empty. The energy released was not diminished by the absence of witnesses. The rupture did not adjust its magnitude to match the population. It released the same force into ground that happened to hold almost no one. That accident of timing is why the 1857 event appears in textbooks as a geological data point rather than a defining national catastrophe. The energy was identical. The losses were not. The geology is not interested in the difference. Pallet Creek runs through the Mojave Desert 80 miles north of Los Angeles. It is an unremarkable stream. Brown water, shallow banks, willows in the dry heat. Nothing about it suggests it holds the earthquake record of an entire fault system. In 1975, a 25-year-old Caltech graduate student named Kerry Seith thought otherwise. C dug his first trench across the creek bed at a right angle to the San Andreas Fault. He was looking for something no one had found before. A written record of past earthquakes, set down not in ink but in mud. The principle behind it is direct. When the fault ruptures, the soil layers on either side of it shear past each other. Peat, the compacted organic material that accumulates in marshy ground over centuries, preserves the exact moment of that shearing. Each rupture cuts through the layers at a diagonal. Any material sitting above the cut is younger than the cut itself. Radiocarbon dating assigns a year. Count the cuts, and you have counted the earthquakes. The work was not elegant. C shoveled by hand. He brushed each exposed layer with a paintbrush. He photographed every centimeter of every wall. He logged each carbon sample by hand and sent them out for dating one by one. There were no shortcuts. The creek bed did not give its record up quickly. A year passed, then 5, then 10. By 1988, C had identified 10 major ruptures of the San Andreas Fault going back to the year 670 of the Common Era. 13 years of trench work to count 10 earthquakes across 13 centuries. The intervals between ruptures varied considerably. The shortest gap was 45 years. The longest was 300. The average across all 10 events came out to 135 years. The last rupture recorded at Pallet Creek was 1857. The Fort Tejon earthquake. The same event that had rolled through the garrison at breakfast, slid the creek bed sideways, and killed one person in a California that barely existed. That rupture was 169 years ago now. The fault has overshot its average interval by 34 years. That number was uncomfortable enough. Then C turned his attention south. He shifted his focus to the Salton Sea segment, working through sites at Indio and along the Coachella Valley. He partnered with a younger researcher named Lisa Grant, who extended the chronology further into the southernmost section. The peat layers there told a different story than Pallet Creek. The last full rupture on the southern section did not date to 1857. It did not date to anywhere near 1857. The radiocarbon samples placed the last major event at approximately 1680. Not the same earthquake. Not the same section. A separate rupture on a separate clock. More than 170 years earlier than Fort Tejon, and more than 340 years ago now. The plate motion is constant, 2 inches per year. It does not pause during droughts or elections or wars. Multiplied across the years since 1680, the cumulative slip deficit on the southern section reaches 20 feet. That is the height of a 2-story house, stored as strain energy in locked rock beneath the desert. Small earthquakes do not release it. They account for a fraction of a % of what accumulates. The rest waits. It has only one direction to travel, and only one mechanism to release it. C published the core findings in the journal Science in 1989. The seismology community absorbed them slowly. The southern section had the desert, the Salton Sea, and a number that was easier to set aside than to answer. The southern section had overshot its average by more than 2 centuries, and the number waiting in the rock was 20 feet. 2008. The United States Geological Survey convenes 300 experts from seismology, engineering, and crisis management to examine a single critical question. What does a magnitude 7.8 earthquake on the southern San Andreas Fault actually do to Southern California? Not in general terms, not in broad strokes, minute by minute, system by system, in the first hours and days after the ground moves. The lead scientist is Lucy Jones, a seismologist who has spent 3 decades studying this fault. The project is called ShakeOut. The scenario is specific. The epicenter is Bombay Beach, a small settlement on the eastern shore of the Salton Sea, sitting almost directly on the fault trace. The rupture begins there and travels northwest at roughly 2 miles per second. San Bernardino is 90 seconds away. The outer edge of Los Angeles is 2 minutes away. By the time the rupture stops, it has covered 300 miles of fractured rock. Strong shaking lasts between 40 seconds and 2 minutes depending on location. In the sediment basins beneath the city, seismic waves resonate and amplify. The shaking there outlasts the rupture itself. The first system to fail is gas. 600 natural gas pipelines rupture across the basin simultaneously. Ignition is not a question of if. Sparks from downed electrical lines, open pilots on water heaters, restaurant kitchen equipment still running at 10 in the morning. Within 10 minutes of the rupture, 1,600 fires are burning at the same time across Los Angeles County. The county fire department has 32,000 personnel. They are not facing one fire or 10 fires. They are facing 1,600 fires surrounded by collapsed buildings, blocked roads, and hydrants with nothing behind them. Mutual aid from neighboring counties takes days to arrive. By then, the fires have done most of what they are going to do. The second system to fail is water. 3 aqueducts supply Los Angeles: the Colorado River Aqueduct, the Los Angeles Aqueduct, the State Water Project. All 3 cross the San Andreas Fault. All 3 rupture in the first minute. The ShakeOut report estimates 6 months before water service is restored to the full basin. 6 months. The fires burning across the city will have no pressure in the hydrants feeding them. Hospitals will operate without running water. The 24 million people in the region will need outside supply for half a year. The third system to fail is transportation. Bridges drop. Overpasses pancake onto the roadways beneath them. The ports of Los Angeles and Long Beach, which handle roughly 40% of all containerized imports entering the United States, halt operations. Supply chains serving the western half of the country pause at the same moment. Fuel, medicine, food, anything moving by truck through Southern California stops moving. The economic damage in the ShakeOut model reaches $200 billion before the fires are counted separately. Counting the fires, the figure climbs further. Casualties on the first day reach 1,800 dead and 50,000 injured. Hospitals across the basin are overwhelmed within 90 minutes of the rupture. Trauma centers that would handle mass casualty events are themselves damaged. Staff cannot reach facilities because the roads are blocked. The injured cannot reach care for the same reason. The scenario assumes a Thursday morning in November. That timing is deliberate. Schools are in session, which means children are in reinforced buildings rather than unreinforced homes. The freeways are past rush hour, so fewer cars are on elevated structures when the overpasses fall. A Friday afternoon, a Saturday night, a summer morning, the casualty figures shift accordingly. The ShakeOut report was 308 pages long. It was distributed to every emergency response agency in California. The opening sentence of its executive summary did not describe a possibility. It described a certainty with an unknown date. The authors described the scenario as conservative. Speaking of faults nobody talks about, there's one beneath the Pacific Northwest that makes San Andreas look like a minor inconvenience. We'll get to that. Subscribe and turn on notifications, or just find out about it when it happens. Now back to the fault. Because ShakeOut called their scenario conservative for a reason. There is one section of the San Andreas that scientists discuss the least, because the arithmetic behind it is the most uncomfortable. The San Gorgonio Pass sits roughly 90 miles east of Los Angeles, where the San Bernardino Mountains press against the Little San Bernardino Range. 3 separate fault strands converge there. The geometry is not clean. Where the rest of the San Andreas runs as a single identifiable seam, San Gorgonio is a knot. The strands overlap, bend, and splay into a zone of fractured rock that no historical rupture has ever fully threaded. What happens when a rupture tries to propagate through that knot is the question no scenario has comfortably answered. In 2012, seismologist Hiru Kanamori at the California Institute of Technology examined what a full propagating rupture through San Gorgonio would look like. The ShakeOut scenario had assumed the rupture would stall at the knot. The southern section would break. San Gorgonio would absorb the energy. The central section would not participate. Kanamori's analysis challenged that assumption. If the rupture propagates through the pass and continues into the central section, the event does not reach magnitude 7.8. It reaches magnitude 8.2. That is not a modest difference. Magnitude scales are logarithmic. A magnitude 8.2 releases roughly 10 times the energy of the ShakeOut scenario. Surface offsets along the rupture trace reach 30 feet in some models. The ShakeOut authors had described their scenario as conservative. Kanamori's paper suggested they may have been correct for the wrong reason. Thomas Jordan, director of the Southern California Earthquake Center, has argued for years that slip deficit is the most underappreciated number in American earth science. The number is specific, measurable, and geometric. It is not a probability, it is an amount. Wherever the plates are locked, the accumulated motion is stored. It releases in the same direction it was stored, across the same surface, in roughly the same amount per rupture. Jordan's point is that the uncertainty is not in the physics, it is in the timing. What a house sitting directly on the fault trace experiences is not collapse in the conventional sense. The structure does not fall, it splits. The foundation on one side continues northwest with the Pacific Plate. The foundation on the other side stays with North America. The two halves end up separated by 20 feet, standing on opposite sides of a new cliff that was not there 90 seconds earlier. Roads crossing the trace are severed at the same moment. Buried pipelines shear along the same line. Fiber optic cables carrying financial data, emergency communications, and internet traffic cross the fault in dozens of places and fail simultaneously. Airport runways at facilities east of Los Angeles cross the fault trace directly. Laser surveys across the Carrizo Plain have mapped stream offsets ranging from 12 feet for the most recent ruptures to 450 feet accumulated across thousands of years of repeated motion. The pattern is not random. The streams do not bend in different directions at different times. They bend in the same direction every time. Each rupture moves the land in the same direction, by the same kind of amount on a schedule the rocks have already written. GPS satellites continuously track the plate motion as it unfolds. These satellites operate with extraordinary precision, maintaining their measurements through decades of continuous observation. The technology relies on networks of ground-based receivers that triangulate positions relative to orbital transmitters, creating a three-dimensional map of movement with millimeter-scale accuracy. Scientists have deployed these networks across fault zones worldwide, from California to Japan to New Zealand, each station functioning as a permanent witness to tectonic displacement. The data streams back constantly, creating an unbroken archive of motion that transcends human timescales and political cycles. The instrumentation itself has evolved significantly since the first geodetic measurements began in the 20th century. Early surveyors used theodolites and measuring chains, methods that required years of comparison to detect meaningful displacement. Modern GPS networks compress what once took decades into months of observation. A single receiver can now establish position to within centimeters. And when multiple receivers work in concert, they resolve movement down to individual millimeters. This technological leap has transformed our understanding of plate tectonics from an elegant theory into quantifiable, measurable fact. Engineers and planners now have access to data that reveals exactly how the Earth beneath their projects continues to shift and strain. The annual displacement reads 46 millimeters per year, consistent to fractions of a millimeter, year after year. This consistency might seem surprising given the chaotic appearance of tectonic processes. Yet plate motion follows predictable patterns determined by vast convection currents in the Earth's mantle. The Pacific Plate and North American Plate do not accelerate or decelerate based on human activity or seasonal variation. They move at rates established by deep planetary physics, rates that have persisted for millions of years. Researchers have compared measurements from the 1980s with those from the 2020s and found the rates unchanged, confirming that current displacement tracks with historical averages extending back through centuries of indirect measurement. The plates do not slow down during construction cycles. Building a hospital, a school, or an apartment complex creates no drag on the tectonic machinery. The contractors may work carefully. The engineers may stress test their designs. The city officials may inspect each phase, yet the plates continue their measured journey. Reinforcement does not impede them. New earthquake standards and building codes do not persuade them to pause. The tectonic system operates independently of human engineering timelines, indifferent to the schedules of fabrication plants and concrete pours. They do not pause while retrofit schedules are debated in city council chambers. Meetings convene, experts present findings, residents voice concerns, and still the displacement accumulates. Whether a city council approves a seismic retrofit in 2 months or 10 months, the plate motion continues uninterrupted. The Earth will have moved another 3 to 4 millimeters during that discussion, inches per decade, regardless of municipal deliberation. This inexorable reality forms the foundation of earthquake resilience planning, acknowledgement that motion cannot be stopped or negotiated, only accommodated and prepared for. The measurement continues regardless of what has been built above it. Freeways span the fault line, their concrete cracking in patterns that mirror the displacement below. Shopping centers, hospitals, and residential neighborhoods occupy ground that shifts imperceptibly, year by year. The GPS stations beneath them record this movement faithfully, documenting the strain that accumulates with each passing season. These measurements serve as the baseline for understanding how much stress the Earth stores, how close it moves toward the next major release of energy, and what safety margins remain before that accumulated strain exceeds what structures can withstand. 3 sections of the fault reveal this pattern, each progressing through a different stage of its cycle. The northern section last ruptured in 1906. The central section last ruptured in 1857. The southern section last ruptured in 1680. 3 clocks, 3 accumulating deficits, 3 ruptures that have not yet arrived. GPS satellites measure the motion continuously. Every quiet year adds 2 inches to the slip deficit on each locked section. Every quiet decade adds roughly the height of a small adult. Every quiet century adds the length of a city block, stored in rock, waiting. The measurement is precise to fractions of a millimeter. The accumulation does not pause. It does not respond to building codes or retrofit schedules or government reports distributed to emergency agencies and left on shelves. The implications multiply with each passing year. Every moment of stillness on these sections corresponds to accumulated strain that must eventually be released through sudden, violent movement. Physics allows no other possible outcome. The question is not whether the ruptures come. Paleoseismology has answered that. The trenches at Pallet Creek answered that. The peat layers at Coachella answered that. The question is which section moves first, and whether the rupture propagates northwest through the San Gorgonio Knot into the central section, doubling the length of the break and raising the magnitude from 7.8 to something the ShakeOut scenario did not model. The question is how many of the 7,500 unreinforced concrete buildings absorb 30 times the energy of Northridge before the ground stops moving. The question is how many of the buried aqueducts, severed pipelines, and blocked freeways remain out of service when the 6 months without water begins. The fault is moving tonight. Not as a metaphor. Literally. Measured in nanometers per second. The Pacific Plate is sliding northwest past the North American Plate along 800 miles of fractured rock. The slip that cannot happen at the locked sections is recorded instead as elastic strain in the crust. The crust bends. It stores the energy. It has been doing this since 1680 in the south, since 1857 in the center, since 1906 in the north. The arithmetic runs forward on its own. No agency is required to continue it. No decision is required to accumulate it. The 3 clocks do not need to be wound. 1680, 1857, 1906. The 4th date still awaits its moment.